So we had a homework session prior to this, which was led by Wenchang,
Uh-huh.
and there I think we ended with chapter 9, if I'm right. So, so is it okay if we start with part 2, that is chapter 10, with neural networks and deep learning?
Yeah, fine with me.
Yeah, it's fine with me too.
Okay. Okay, just give me 2 minutes.
Mm-hmm.
I'll just take out my book as well.
Yeah. Yeah, it will provide us a good opportunity to just go over what we have already studied, and then neural network, that's the most important part. So yeah, it's a good idea.
Yeah. It's always important to uh, go through the questions to see if you have actually understood everything, and even the coding part.
Correct. Yeah.
It will be really useful.
Yeah.
Okay, I think we have actually done chapter 10. So I think we should start with chapter 11. Is there anything in chapter 10 that you guys want to discuss? You can maybe quickly go through that.
I was not part of homework for a while, so
Yeah.
and say for same reason, like I didn't do any homework because I wasn't a part, and that's the big reason for me to have a part of one of the sessions so that I can do the homework.
Okay, I think then we can quickly go through chapter 10 if that's okay with both of you. I mean, yeah,
Fine
since
with me.
Dinesh was not part of the.
Yeah, it's fine with me. It might be good to go over. I don't really remember what we did in chapter 10.
Yeah.
Can one of you open up the actual answers given in the textbook and maybe read it as we finish with each question? Like once we discuss it, is that, I mean, can either of you do that?
I'll be able to do it. Yeah. Yeah.
Okay. Okay, that's great. Okay, then we can start off. The first question is the TensorFlow Playground, which is that website where you can uh, like play around with different types of sample data that they have, and yeah, and you can just see how strong or weak the classifier becomes as you change these hyperparameters.
Yeah.
I'm not exactly sure how to use it. And have any of you actually played with this before?
I don't know how to make full use of it, but I think like, you can add, so as you're doing like neurons or change the activation up there. So, and then if you press play, you can see it like train. And for however number of epochs you want, so you can see. And then if you pause it and change the activation function, you can see like how it might impact your end. So you can see like so you see like this one's a bit more angular than 10H. Like
Okay, I actually never knew that having ReLU as activation would give you classification boundaries that look more polygonish. Okay.
Yeah, I didn't know that either. This was like when I was just doing it for, I think I only spent like 10 minutes on it, but that I found that too, and it was really cool actually. And you can add, of course, like more features, right? So like not just x1 and x2, but like x1 times x2, or yeah, other, and see how it changes your end result.
So this X1, 2 is the product of these features?
I
Okay, it's
really
not
don't know what
something else.
x1 2 is
Yeah,
actually.
it
They
is. It
have
is.
separate X1. No, they have separate X1, X2. So this is the product.
Yeah, this is a product.
So probably x1 by 2 is like x square.
What's that?
It's probably the x square.
Oh, okay, okay. Yeah, that's
I see. Yeah,
yeah.
okay, that makes sense.
Hmm.
And one of the important point I was reading somewhere is that um, once you go from a simple to more complex problem, and on your left, if you look at the data, you have the data like a 4 data sets, 4 different kind
Yeah.
of data sets given to you. So
Yeah.
interestingly, instead of a deep one layer model, if you have this shallow more layers, it converge faster, and it's give you more optimal solution. And interestingly, what they said, I read somewhere, I'm not sure where, they say, the back in the days when they used to do the neural nets, they kind of like a stuck on the one layer shallow network, and it kept on trying, and that's why they didn't progress for decades. And all of a sudden they discover that if the network is a deeper, uh, the problem gets solved quicker. So they say, however, it's the combination of a two. It's not one way or another. However, it's if you add one more layer, I think your solutions start getting quicker to converge.
Hmm. Okay. Yeah, I mean, I think it should have been obvious, right? Like adding one more layer should. Why did it take a decade for them to
I mean,
do
like
that?
this is interesting. I think the focus initially was that they thought the more like
Okay,
deep.
maybe they did not have activation functions at that time, right?
I-
Okay, they had step function or something. Yeah, they had some weird
mm,
activation functions. Yeah.
mm,
Because
I
when
think
you
they were
don't
also
have
a little bit,
activation,
I think they were also like a little bit limited by computation power, which is not.
correct. Correct. The
yeah.
data was data and a computation. You're right. Like it's not just a one way. Uh, there were so many factors, obviously.
Also, like I find sometimes like you need like one person who is really big in the field to say bad things about the thing, and then no one will follow it for another 20 years, and then you need somebody else to come along and be like, oh, this is actually cool, for people to put like money and effort into it. So it's like depends on how much PR it gets from like other people who are big in the field.
So anybody knows like what was the cause? Who was that person? Like, why did it go into like the cold storage for so long?
I'm not
I
sure. I don't know for this one.
I guess things it I mean it never really worked that well, right? That was
yeah.
probably the reason. It never really worked for a lot of the problems. So they
Mm,
just put it on the back burner. And
Mhm.
then Jeffrey Hinton came up with backprop in 1980, mid 80s. I think that's when it s- gained some more promise.
mm,
Then it died again in 90s and 2000s. Then it came back in 2012 and so on
mm.
with the ImageNet success and all of that. I think SVMs were the hot thing in late 90s and 2000s. SVMs, random forests. Yeah.
That's correct. Yeah.
They're still quite
Even
popular, I think,
yeah,
at least in
Yeah.
academia.
yeah. The Kaggle was big. Even uh, initial winners, they tend to do the SPM quite a lot there.
Mhm.
But now it's all
Even
more.
now, yeah, I think like Maria said, even now probably random forests are popular in the industry. like we are biased because we are exposed to neural nets more. Maybe in outside they still use a lot of XGBoost and random forest, probably decision trees.
Potentially, yeah,
Okay.
correct.
Okay, are there any interesting questions here? Take some time to explore the patterns learned, activation functions. I think we know all of this, right? We can replace
Yeah.
the tanh with ReLU, and we saw what happened after that. Notice that it finds a solution faster, but this time the boundaries are linear. Okay, I actually did not know that. Hmm. That's very interesting.
Mhm.
The risk of local minimum modify the net.
The question on the activation function, is the activation function, is this sort of like given now that ReLU is going to work most of the time on the neural net, or there is a like it based on a problem that you use ReLU or a 10H or softmax?
Okay, the problem with so tanh and sigmoid have certain specific problems because of which we avoid using them. Like sigmoid has this thing, the vanishing gradient, because it
Yeah,
kind of flattens out, right? So
correct.
actually, the reason why neural nets work is because of a theorem called universal approximation theorem. So what that theorem says is you can have any nonlinear function and it should actually work. And even Jeremy talks about this. He says that any so this I'll just read the definition. So any type of function can be learnt given that okay, this is slightly complex definition. So what it basically says is you can learn any type of function uh, given you have some kind of matrix multiplication followed by any nonlinearity, and uh, you give it enough time to actually converge. Yeah, so that's
So in a sense, the ReLU, we use ReLU because it's converges faster.
uh, no, it's a nonlinearity. ReLU is a nonlinear function, first of all, and its slope is easier to compute compared to others, and it does not have the this thing vanishing gradient problems that tanh and sigmoid have. So it just
Yeah,
happens to be more efficient in,
most efficient. Okay.
yeah. But
Yeah,
according to this theorem, any nonlinear function is enough.
yeah, but
Like
that
a matrix
that
multiplication followed by any
the
nonlinear function, you can learn any type of function. Yeah.
yeah. So the 10H would be the nonlinear, the 10H
Yes.
or
Yes.
like the sigmoid. But as you said, it's more of like then we're looking more into efficiency side of it.
Yeah.
ReLU is also nonlinear.
Yes. Yes.
Yeah.
This is
However,
also nonlinear. Yeah.
yeah. However, this is interesting. Like after the ReLU, the functions like a CELU or a leaky ReLU, all those functions came in. However, we still like if when you read this book, and if you look at the example, he has used Celio quite a lot. However, when you look at the example on a wide, like let's say TensorFlow, anybody or everybody I am seeing use Relio. So hence the question, is it like kind of like universally taken that ReLU is the de facto non-linear function in neural network, or does it based on the problem to problem?
I think there's some discussion about this in another chapter. Let me just find it quickly.
Yeah.
Actually, I think it was in this chapter, actually.
I'm not sure I know the answer to that. Like, yeah, your question is interesting. Does the activation function actually depend on the type of problem we are trying to solve? But if you notice the newer architectures, the newer models that we have, like even Bird does not use ReLU. It uses something else, CELU, GALU, I'm not sure, some other thing. So yeah, these slight modifications to ReLU are the more popular ones. in the newer architectures.
But this is interesting because I'm saying other way around. I'm
Okay.
saying that the SLU and a leaky ReLU I have just read in a text, but
But you've
when you
never
look,
seen them.
haven't seen them. Like any example, any sample notebook comes in, even whenever like Jeremy's whole lecture, he's using just one activation function, ReLU.
Yeah. So BERT uses GLU actually. BERT does not use
Uh,
a ReLU. it's it's in the activation functions that we usually build. I mean, the neural nets that we usually build, we just default to ReLU all the time. I think it's
uh,
time that we also start using GLU and
Cardio.
the other ones. Yeah.
Mhm.
And the thing is, as with many other things in neural nets, there is no good explanation of why something works better than the other, right? It's all empirical and
Correct. Correct.
yeah.
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 Yeah, it's hard to look as well. I did experiment with all this ReLU, SLU, and GLU in one of I think Kaggle competition I was doing. So all I was doing is just changing the activation function, but obviously it didn't help much.
Okay.
Okay, so sorry, on page 338 of the book, so I think that's chapter 11, just before batch normalization, he kind of tells you a little bit. So he says, so which activation function should you use for the hidden layers of your deep neural networks? Although your mileage may vary, in general, SALU is better than LU, which is better than leaky ReLU and its variants, which is better than ReLU, which is better than 10H, which is better than Logistic. But then it like tells you maybe why it might not be appropriate to apply SALU or the others.
Okay.
Yeah.
Page number 338.
Yeah, 338 is like a little sidebar, I guess.
Yeah,
So.
yeah, I can see it.
Yeah, this one,
So
right?
it tells you like why you might want to use other why you might want to use ReLU even though it's not as good or yeah. Well, it gives you a little bit intuition. I don't think it tells you. I don't think it goes into enough detail, but
You can use a cross validation to
Yeah,
evaluate other activation function.
yeah, that's funny.
Go back to the basics.
Okay, what is R ReLU? Not heard of that. P ReLU. Okay.
he doesn't really go into enough detail into those.
Okay. It says hardware accelerators provide ReLU specific optimizations. ReLU is just max of 0, comma x. What optimization do you need for that? Okay. I think you can move on, right?
Mm-hmm.
Yeah.
Yeah.
What happens when neural nets are too small? Remove one neuron to keep just two. Notice that neural network is now incapable of finding a good solution, even if you try multiple times. Okay, yeah, that makes sense. What happens when neural nets are large enough? Set the number of neurons to 8 and train the network several times. Notice that it's now consistently fast and never gets stuck. This highlights an important finding in neural network theory. Large neural networks almost never get stuck in local minima. Even when they do, these local optima are almost as good as the global optimum. However, they can still get stuck on long plateaus for a long time. Okay.
So how come deep network, large network? When he say large networks, he probably means like both deep and wide then. They never get stuck into local minima.
I think he means deep. Because like, there's a specific thing, deep and wide is a specific type of network, isn't it?
No, he's large.
No, Dinesh is just saying like more layers and more neurons in each layer, right? More nodes in.
Well, that's what I'm saying when he said large network.
So in this particular example, he says set the number of neurons to 8. So it's just a wider network. That's what it looks like. Any of you have any good intuition of why a large network won't get stuck in local minima?
That's exactly my question is.
No, not really.
Okay, so large network. You have more weights, more biases.
Okay, one thing I can think of is so yeah, so large network has more parameters, and so this is something I read a long time ago. So when you have more parameters in a vector space, so to have a local minima, you need to have gradients that increase in all directions, right? That makes sense?
Yeah, that does.
So when the large, so if you have millions of parameters, the chances of a local minima actually occurring is very, very small. Whereas if you have lesser number of parameters, the chances of a local minima, this is actually very difficult to visualize since our brain is quite limited. But the chances of a local minima occurring in your loss function is higher when you have lesser parameters.
Yeah, that
Does that
does
make sense?
Yeah.
It's kind of intuitively because you have a more parameters. The more parameters are that the you have a lot more weights that it's not going to get stuck. So in a sense, all the weights working together to get you to some minima, and obviously because you have a huge number of the weights, so they're going to work in conjunction, and then the goal is to get you to the global minima rather than get anywhere get stuck into local minima. You know what I mean?
Yeah.
Because local minima would be you take a small step and you get stuck because you have just a few parameters to tweak it. But when you have like a millions of parameters working, you will never able to get stuck in there because you even won't get there because the parameters are going to work in conjunction with each other like a scrum. That's the intuition I'm getting without picturing anything, you know. Am I making sense?
I'm not sure of that, but the point I was making was slightly different actually.
Go on.
Yeah, it's the same. Like, so you have to, so the loss function that we are trying to minimize,
Yeah.
I mean, it is plotted as a function of the parameters itself. Like,
Exactly.
so you
Yeah.
have W1, W2, W3, and then you have weight is plotted. I mean, sorry, not the weight. The loss is plotted as a function of W1, W2, W3, and all of that, right?
Yeah.
So what the point I was trying to make is to have a local minima, at that point you should have increasing gradients in all directions, which is very unlikely if you have millions of parameters.
Yeah.
So you won't encounter, but I think that is just one uh, that is just one reason probably why local minima is not there, but the other reason might be something similar to what you said, Dinesh.
No, actually, what I am saying is exactly what you said. It's exactly the same thing which I was trying to visualize in my mind. That because you have a huge number of weights and biases, they are working in conjunction to take you to
Mhm.
the a global minima. So you won't
Right.
get stuck into a local minima because you have a huge volume of weights. And as you said, it's
No,
you're
my
going.
point is uh, there are actually no local minimas or very few local minimas for you to even get stuck in. There are no local minimas in the first place, or very few. That's
But
my point basically.
you could have like you could have any number of local minimas. Why would you say that there are no
No.
local minima?
Uh, so why do you get stuck in a local minima? It's because the gradients are all increasing from that point, right? If the
Yeah.
gradient was actually uh, maybe I can draw a quick picture. I'm wasting time surely, but uh, so okay, this is going to be bad.
Mhm.
Uh, okay, why the hell is not painting anything? Ah,
The color of your.
okay, great. Uh, is there a mm, so suppose this is a particular weight axis
Mhm.
and you have a loss function that looks like this.
Mhm.
Okay, so this uh, how do I change the color in this? Okay, so this is the global minima, right?
Yeah.
Mhm.
And this is your local minima.
Yeah.
So the reason why you get stuck in local minima is the gradient is increasing this side and this side.
Yeah.
So even if you do gradient descent, you are just going to be, I mean, your model would still, your weight updates would still be, uh, will lead you to be remaining in that place itself, right?
Correct.
Like, yeah, gradient descent won't help because the gradients are increasing on both directions.
Mhm.
So, uh, so what I'm saying is when you have millions of parameters like this W1, you had W1, W2, W3, the only time when you get stuck in a local minima is when you have gradients that are increasing for all the weights. Even in W2 direction, W3 direction, W4, W5, in all directions, your gradients should be increasing. And the chances of that happening are very less. So that's just a property of a high dimensional thing. It's difficult for us to visualize that. So
I
even if in a single direction your gradient happens to be dropping, your gradient descent will take you in that direction, leading
yeah.
you to not get stuck in a local minima.
Mm.
You get to escape out of the local minima.
Yeah.
Yeah, that was the point I was trying to make.
Okay. Okay. However,
So yeah, so basically the chances of a local minima happening are less because
yeah. Okay.
yeah, the gradients uh yeah, they won't be increasing in all the million directions. They're
Ah,
probably, yeah, that's my point.
okay. I get it. I get it. What you're saying. You're saying like it won't even get near to any local minima whatsoever. It's gonna go in the direction of global minima automatically.
Yeah.
Yeah.
Okay.
Good discussion.
Yeah.
Mhm.
Mm, yeah, but plateaus are possible in, yeah, they can get stuck there. Okay. The risk of vanishing gradients in deep networks. Select the spiral dataset. Change the network architecture to have 4 hidden layers with 8 neurons each. Notice that training takes much longer and often gets stuck on plateaus for long periods of time. Hmm. Also notice that neurons on the highest layers. on the right tend to evolve faster than neurons on the lowest layers on the left. This problem, called the vanishing gradients, can be alleviated with better weight initialization and other techniques such as Adagrad or Adam or batch normalization. So vanishing gradients is basically when your slope becomes very close to zero. So your weight update does not happen. It remains stagnant.
Yeah.
So yeah, your loss is also remains in the same level, does not decrease as fast as you would like to. So one option to alleviate that is better weight initialization. So you start at a better place and you are less likely to encounter vanishing gradient problems. And better optimizers such as Adagrad or Adam. So these optimizers will help you quickly escape that the plateaus and reach the global minima. That's how I understand this.
And this vanishing gradient, so does it have anything? Yes, so normalization is the same thing. When you is the scaling of the features, when we scale the features,
Hmm.
does it has anything to do with the vanishing gradient problem?
Yeah, that's what they say here. Mhm. But I'm not sure how batch normalization helps in the problem of vanishing gradients. Uh,
Yeah, because the whole idea is that to keep the all the feature in the range of like a 0 to 1.
hmm. I think we did see why we should normalize the inputs, right? In a previous chapter
Yeah.
or in the same chapter. The logic is probably the same thing. So instead of normalizing the inputs, you are normalizing the values at an intermediate layer.
Yeah.
So probably the logic is the same.
Logic is the same. You're
Yeah.
right. So I think this first we do the normalization of the features. However, because with the back propagation, the weights are going to be changed. So the weights are now going to go be up and down. So I guess this is to keep those weights in a check between those range values, not to either go minimum or either go exploding.
Yep.
That probably is the batch normalization part.
So do you guys remember where that diagram was? So there was a picture, right? Showing what happens if you don't normalize your inputs. So
Yeah,
it takes much longer to learn or something like that.
I think it was much earlier. Hold on. I think it was in chapter 4.
Oh.
Chapter 4.
It's great that you remember the chapter number even. Okay.
I think, no, I just have the table of contents in front of me. I think it was page 120 actually. If I'm thinking the same one that you are, figure 4.7.
The 20.
Yeah, that's the one.
Figure number, which figure look you're
Four
looking?
seven. 4.7.
4.7. Yeah.
Yep. This is the one.
This is gradient descent with and without feature scaling.
Yeah.
Hmm.
So the gradient of the gradient of theta 2 is dominating in the figure on the right, and the gradient of theta 1 is much smaller. So that's why the direction of the descent is curvy in that way. Whereas if both had the same scale, the
Yeah.
gradients would be optimal and we would be on a quicker path. Yeah.
Yeah. So that would be the feature scaling.
Yeah. And
So,
the logic is the same, I believe. So
so once we have done the scaling, and then the feature gone into the like in a batch, and then we start training. Then we do the batch normalization. So
yeah.
the batch normalization is the normalization of the weights.
No,
It's
it's the normalization of the node values, the activations at an intermediate layer. So you can see the diagram, right?
yeah.
It's like you are normalizing these two values. Just assume that these two are inputs to a neural net that lies after it, and you are normalizing these two.
Again.
It's yeah,
But the outputs from those two.
Okay. Yes.
yes, yeah, the activations, yeah,
The activations.
Yeah, the activations. Yeah.
Yeah. It makes sense because we want to keep them in control, because we're going to apply the gradient descent to them, to the
hmm,
activations. They need
yeah,
not to go. No, I think I got it. When you said activation, that makes sense. Yeah.
yeah. And regarding batch normalization, also, I think there was some controversy as to why they actually work. Uh,
Yeah.
you remember that? Even
Yeah.
Jeremy mentioned that.
Mm-hmm.
So Jeremy basically said they were wrong, and the reason why it works is something else and not what they said in the paper, something like that.
Correct. I read even a paper. So they say the batch normalization work with the covariance. So I think they kind of like fix the covariance. That's the assumption. But there are few papers, as Jeremy said as well, like they say, oh no, it's not the covariance. So the claim has been disputed. However, it still works.
Yeah.
Mhm. Yeah, I think like as Jeremy explains it, like it makes the loss landscape a little bit smoother. Um, so like it's not as bumpy, so you're not getting stuck.
Hmm.
So like the training is easier. But I don't know if that answers your initial question of like how it helps the vanishing gradients problem or the exploding
Hmm.
gradients problem.
Yeah. Yeah. If your loss landscape becomes smoother, then your gradients are also stable, right? They won't vanish.
I
Mm.
guess, yeah, that's true.
So when we say loss landscape get smoother,
Mhm.
expand on it. Like what does the like loss landscape means? What does it mean this time?
So it's like the function, right? Your loss function is a function of your weights, right?
Uh-huh.
Um, so if you have your mean square error, let's say for example, it's a quadratic, right? So it has, that's the loss landscape in that case. If you have just one parameter, let's say, yeah, in like one dimension,
Mm-hmm.
it has that. But if you add, it's just like what that function looks like with however many parameters you have, right? So it's kind of difficult to picture it in more than 3D. So picture it with more than two weight parameters. But I guess like MSC with two weight parameters kind of looks like a valley,
Mm-hmm.
you know.
And
But if
the
it's like more complicated, then it might be more bumpy, or at least that's how I imagine it.
when you say bumpy, does it means then when we are descending down, we are descending slowly and in one direction, uh, just down, not the zigzag down.
Um, when I say bumpy, I mean the opposite. I mean like, you might, maybe overall you're going down, but you might have to climb mountains and then descend them,
Uh-huh. Uh-huh.
yeah. So yeah, bumpy is like yeah, the overall trend is to go down, but you have to go up and down a little bit, like
You're spiking up and down.
yeah. So
If
it's,
it's going
which
down,
is what would, you know, like Gautam just drew that picture for us. So like that was a little bit, I mean, it was not super bumpy, um, but you know, like there was that local minimum. Yeah, so like it's sort of bumpy. It's not really. It's fairly
yeah.
smooth, but um,
So doing batch normalization makes it a smoother ride without these bumps.
yeah.
Yeah.
Right. Yeah.
Yeah.
Yep.
Got it. Thanks.
Okay.
And he had that really good picture actually.
Yeah.
Where?
I think I saw the picture. It comes to my mind. It's maybe in one of the paper, but I know what you're saying. Yeah, but it's always good to discuss to get the perspective.
Can I paste a picture in here? No, I can't.
Do you want to share the screen? You can do that.
Yeah, well, it's from Jeremy's course, so I can do it quickly if you want me to.
Okay. Yeah.
This one. Okay. Share. So this was the picture I was thinking of. It's a screenshot from his. So this is from like V3, not V4. But I guess like this is like before. So like you can see, okay, it's going down, the loss is going down overall, but it's like very, very bumpy. But like when you take averages of a little bit, it kind of like instead of it being that way, it's kind of, you know, it smooths it out a little bit more. So it's a little bit less bumpy. So you're less likely to get caught in here. Yeah. Does that sort of make
Yeah, makes sense. Yeah.
Yep.
Thank you.
Thank you. And the loss, the final loss that you reach is slightly lower in batch norm, right? According to the diagram that you just showed.
Yes.
Yeah. Otherwise, there's no point, right? Even if you are bumping, I mean, even if you have a lot of bumps, but at the end of the day, if you reach the same loss, then it doesn't matter, right?
I guess it may do if you reach there quicker.
But in this particular diagram that you showed, the number of steps is the same.
Yeah, it's fairly yeah. But I guess like yeah, that's true.
But I think the batch norm one was slightly lower than the standard one, right? The loss was slightly lower after the same number of steps.
Yeah, it was, yeah.
Then it makes sense.
But there was another picture that he showed, though I can't remember if it was for batch norm or not. Oh yeah, this is a good one.
You want to share?
Well, it's not really. I mean, it shows you a lost landscape, but it's not to do with batch norm, so I don't think it's
okay. Okay. Can we move on to the next question? Draw an artificial neural network using the original artificial neurons that computes. Okay. This thing is hidden for me. Can you see this black bar on my screen on the right side?
No.
Okay. Something is blocking. The zoom has made something on my right side. Okay. So what does it say after that computes A, that thing into B, then in the brackets, what does it say?
Where that symbol represents the
okay.
XOR.
Oh, okay. XOR operation. Okay.
I don't remember what this question was about. Figure 10.3.
Oh, okay. I don't think this question is too relevant.
No, maybe not.
They're asking us to draw the that old style of diagrams. I don't think that's important, right?
Yeah, let's move on.
Okay. Why is it generally preferable to use a logistic regression classifier than a classical perceptron single layer of threshold logic units trained using perceptron training algorithm. How can you tweak a perceptron to make it equivalent to a logistic regression classifier? I think it has to do with the perceptron has some kind of step function activation.
Yeah.
Dinesh, can you read the answer? I
Yeah,
mean,
okay.
if you have anything to add, then either of you can add.
No, I don't.
I
Like,
don't remember this exactly
what
right
was
now.
it? Am I allowed?
Yeah.
Okay, let me read it. A classical perceptron will converge only if the data set is linearly separable, and it won't be able to estimate class probabilities. In contrast, a logistic regression classifier will converge to a good solution even if the data is not linearly separable, and it will
Oh.
outclass probabilities. That's important point. Two important point it had made. If you
Yeah,
change,
actually,
yeah, go on.
no, actually, yeah. We had discussed this in the last. I remember that. So my argument at that time was actually logistic regression is a linear classifier. So how does it? It actually won't work for a non-linear, non-linearly separated data. That was my point at that time, and I'm still not clear on that. Can you tell me what page the answer is on in the textbook?
I have this EPUB,
Okay.
the
Oh,
Apple.
I can tell you. Hold on.
Okay, I got it. It's page
Oh,
731. Yeah,
sorry.
it's okay. Yeah. So yeah, logistic regression is actually a linear classifier. So I don't understand his point of how it will converge to a good solution even if the data set is not linearly separable. Maybe what he means is like a good enough solution, uh, whereas perceptron will completely mess it up or something. I don't know.
So it's perhaps the answer would be it is a linear classifier. However, you may have the exceptions. So it probably linearly separate the data, but not maybe 100%. Is that maybe? Because if you have, let's say, some noise in a data, so it will still separate them, but you may have the exceptions. So if you imagine a line going vertically up, so there might be like blue and red dots. You may find one or two blue dots mixed in the red, and then vice versa. But still, they are separated by linear regression. Um, Perceptron may not be able to do it. That's what I'm thinking.
Okay. No, but yeah, if one or two points are on either side, I think as a whole it would still be considered as linearly separable. So what is not linearly separable is when you need a
Hmm.
like a polynomial, a second degree curve, or something more to
Hmm.
separate. So something like what we saw in this TensorFlow thing.
Oh, yeah.
Yeah, I mean, yeah, all of these are not linear. This is a linearly separable one, the one that you can see right now. None of the others are linearly separable.
No, the first one is, you remember, like if you look at the top left, that the first one is linearly separable because if you create that wall, the hyperplane will divide the This one, yeah. If you click on this,
Yeah, this one.
yeah, this one, yeah. So it should be linearly separable. You know what? If you create the
The
hyperbola,
kernel stuff, right?
sorry,
If you use a kernel
yeah,
Yeah.
yeah.
or but logistic regression won't be able to uh, classify this, right? It would totally fail at this.
I'm not
I mean,
sure. I don't
unless you
So
use some kind of transforming kernel and then do it.
how
Mm.
would you use? How would you use? Do you have any? Do we have like activation function would be the logistic, or it's a
Yeah,
classification?
so it's just sigmoid, right? So
Uh,
all the inputs feed into. So logistic regression is basically exact same as linear, but you add a sigmoid. I mean, you pass the whole output to a sigmoid function.
so activation functions sigmoid you're gonna pass on this TensorFlow playground.
Yeah, that's what I'm trying to do actually. Uh, sigmoid with just these two inputs and start. Okay, why does it not show anything?
Yeah, it's trying to. Yeah, the blue up and then the red below, but that's not good enough.
No, I can add one layer with uh, let's say okay, relu and okay, even now it's actually failing badly.
Mm. So you think it's a misprint that he says that it can be used for nonlinear classification?
Yeah, probably. That's what I feel.
So interestingly, I think I have seen. I played with it and then it did work. But
So if you use either of these features that you see,
yeah.
then yeah, logistic regression can work. The
Hmm.
ultimate model that you create is linear, but if you use these square features and product features, then yes,
Then,
logistic regression can be used for nonlinear data. It is nonlinear in the sense that if you only use x1 and x2, then they are not linearly separable.
hmm.
Okay, is there anything else in that answer that's important to discuss?
Okay, so let me read it out. It's halfway through. If you change the perceptron activation function to the logistic activation function or the softmax activation function, if there are multiple neurons,
Hmm.
and if you train it using a decent gradient descent or some other optimization algorithm minimizing the cost function, typically cross entropy, then it becomes the equivalent to the logistic
Yeah.
regression.
Yeah.
So if you add loss function and as cross entropy and then I add a softmax as an activation, then perceptron becomes your logistic.
Yeah. 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 You can create a logistic regression classifier using using in the neural network approach. Yeah.
Yeah, and that's it.
Okay. Mm. Why was the logistic activation function a key ingredient in training the first MLPs?
Why was the logistic key ingredient in training the first MLPs?
Is it because it provided a non-linearity that can be used to learn complex relationships, basically non-linear relationships? Is that the answer?
Uh,
I was well, maybe it is also, but I was also thinking maybe so you can get probabilities if you have a binary classifier.
Okay.
I do.
I mean, yeah,
have to go now.
you could.
Sorry. I'll see you guys next Monday. Sorry, we'll only be
Okay.
able to stay an hour most of the time.
okay.
Yeah, I didn't know that an hour had passed. Okay. Yeah.
And you're having fun. See you guys next time.
All
Yeah.
right. Next week.
Thanks. Bye bye.
Yes. So it says the logistic activation function was a key ingredient in training the first MLP because its derivative is always non-zero. So the
Okay.
gradient descent can always roll down the slope. When the activation function is steep function, gradient descent cannot move as there is no slope at all.
Yeah. Yeah.
When the activation function is a step function. Okay.
Mm-hmm.
So it's
Got
a
it. Got it.
continuous slope it's providing. That's I think gist of it.
Yeah. 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 That makes sense. Yeah.
Cool.
So, do you want to continue a few more questions, or want to continue with next week?
Maybe let's do next week.
Yeah.
Maybe more people.
Yeah.
Yeah, I'll read through it.
I
But
mean, it's good that, I mean, if we have a team of three, we can discuss a lot, and
exactly,
yeah.
and I
Yeah.
think that's the whole point that y- three of us have a different points, different way
Yeah.
of thinking, and then once we have discussion, 1 hour is more than enough. So it
Yeah.
was a
We
2 hour.
should probably make it a little bit faster.
Yeah, probably. Yes, that's correct.
Yeah.
Yeah,
You
we'll
can
try.
target to finish this, and yeah.
Yeah, next week we try to finish this. We'll finish this and move on to the next chapter next week.
Yeah. But yeah, we don't have to. Is it important to catch up with the
Yeah.
reading group? No need, right? We can go
Uh,
at our own pace.
what I was thinking, my thinking was that if we are on a page like chapter 13 or like a 14, so if we are like around like a one chapter behind, then it's a good exercise to go on. But we can, let's see, because we speed up a bit next week to cover chapter 10 completely and then maybe move on to 11, so we take 1 week for one chapter and then maybe just stay behind them.
Okay. But I'll be busy the next, I mean, I'll be coming for the classes, but later on, if three of us are free at any time, we can just meet maybe on any day. Like if you guys are free
Yeah,
to catch up on discussions and all.
yeah, absolutely, yeah, yeah,
You can start a small chat, maybe, since either maybe other people are not joining, right? We
yeah.
can, if
let's
you want to
let's
discuss
do
anything or
maybe
anything.
yeah, yeah, absolutely, yeah, yeah,
Okay. Yeah.
we can
Thanks.
do that. Yeah.
Yeah. Okay.
All right. Thanks, Gautam.
Yeah. Thank you.